Welcome everybody. This is Back to Basics, RAII. My name is Kostur. I've been working in C++ for almost 30 years now. I work for Arista Networks. We do very large scale switching. I'd like to thank Bjarne for advertising my talk so eloquently during his keynote. You must have noticed how many times in there he mentioned about resource management in RAII. I'm perfectly happy to take questions during the talk, so if you need to ask a question, raise a hand, I'll try to get to you. Today we're going to be talking about what do we mean by a resource, or at least what do I mean by a resource? What issues crop up trying to handle resources by ourselves in C and C++? Introduce the whole idiom of RAII, the resource acquisition is initialization. Show you some of the examples in the standard of some classes that already exist in the library that do RAI type operations. And towards the end, we'll talk about the various considerations about what you want to think about when you're trying to implement your own RAI classes. Because almost inevitably, you will probably try to manage a resource that the standard library doesn't know about. So what do we mean by a resource? A resource is some sort of facility or concept that you gain access to by some sort of acquire and release pair of operations. I'm pretty sure everybody here has probably done at least one type of resource. Memory. That's your classical new on the acquire side, delete on the disposal side. But in addition to just memory, because RAI is about resources, we can also talk about things like POSIX files. And there's your Fopen and Fclose calls to open and close a file. Joinable threads. A stood J thread deals with the create the thread during its construction and joins the thread at the end during its destruction. Locking a mutex is a resource. Lock the mutex on one side, and you want to be very sure you unlock the mutex on the other side. The common problems that will run up when you're trying to manage resources. The first one comes up, leaking your resource. That's where you end up and you lose this handle that you got a hold of. So you no longer have any way of talking about your resource to be able to dispose of it. And depending on the resource has different implications of what happens if you keep leaking it. Leak lots of memory, your program starts consuming more and more memory, you start swapping, eventually the out-of-memory manager might come along and kill you. Not a good thing. Open too many files and forget to close them, you'll run out of file descriptors in your process, and then it won't let you open any more files. If you lock a mutex and forget to unlock it, well, later on, you're going to want to get that mutex again somewhere, whether it's in your thread or a different thread, and that's a short trip to a deadlock. Second issue that tends to pop up, use after disposal. So if you use RAI well, it's very hard to use the resource after disposing it because your resource object goes away. You have no way of talking about it. Same sort of deal with a double disposal. C++ doesn't turn around and destroy objects twice. Not without you trying very hard, at least. So in my example of what comes up, I'm going to talk about using the mutex as the example resource. Let's look at a nice, small slideware type function. Takes in a mutex, takes in some data source that you should have that mutex locked before using it. We start off, lock the mutex. I have some other buffer class that I'm going to read things into. I read from my source into that buffer, show whatever that buffer is, and then return true. And because this function is nice and short, it's not too hard to see the problem we have here. I've locked a mutex, I haven't unlocked it. Right, I acquire the lock here, but I didn't unlock the mutex, so it stays locked permanently. The next time someone calls this function, your program comes to a screeching halt. The next time someone tries to lock that mutex somewhere else that wants to talk about that data source, comes to a screeching halt. Easy enough to fix. I can add the unlock. We're good, right? Lock, unlock. But as you may notice, this function I have returning a bool, because it might fail expectedly. That read into buffer, for example. I want to now test to make sure that, if I fail to read, I want to return false for my function. Well, I've just reintroduced the problem we just solved. Now I'm again doing an early return from this function. My mutex was forgotten to be unlocked. Okay, I can fix this again. Add in my unlock. We're happy again for a while. What happens if reading into a buffer throws an exception? Here we go again. Your function exits. I have forgotten or forgot to unlock the mutex. Recipe for deadlock. Okay, this is still solvable. Add on a try catch block. Try, catch every exception that could possibly happen, unlock the mutex, and since I have nothing better to do with that exception, rethrow it so somebody above me can deal with it. But hey, at least I'm thinking ahead a little bit. If display throws an exception, I'm still protected. Why don't we have this sort of leaking problem with the contents of a vector? Right? Vector's got dynamic memory, it allocates stuff. Why don't we ever leak memory from vector? Because it behaves with C++ object lifetimes. See, in C++, our objects begin their life at a defined place, and they end their life at a defined place. We even have functions that get called, and I'll use the term call loosely, gets called on these two places in time. We have constructors on one side, destructors on the other. And the language will ensure that these get called. I don't have to remember to do it. For at least in the beginning of this talk, we're going to look at specifically objects with automatic storage duration, also known as local variables. And this is where the RAII idiom, the core of it, comes in. In the purest sense of the term, this is the idiom where we acquire a resource during the constructor of an object, and we dispose of the resource during its destructor. In my opinion, it's somewhat of a misnomer, because I think that really the destruction side of this is the really important part. Coupled with this idea is the concept of the ownership of a resource. Who actually is responsible for it? When you call new, new hands you back a pointer, and at the same time is essentially handing you the ownership. I don't want to own the resource. I want to hand that ownership off to the RAII class, make it responsible for the resource. Standard library has a number of RAII classes in it. The first one we want to take a look at, because it applies to my little sample program, is stood lockguard. Lockguard is a standard RAII class that its job is during its construction will lock the mutex, during its destruction, unlock the mutex. That way I can't forget to do it. So using this, we can look back at our function that we just finished enhancing to make it bulletproof so it always releases the resource. And let's modify this to actually use that RAII class to manage my resource instead of me being responsible for that resource. So of course, first off, replace that mutex lock with declaring my lock guard taking the sum mutex. I have now, this will acquire the mutex. Now that I don't need to use sum mutex, let's look at all the other places we talk about sum mutex, because those should be no longer required. I no longer need to unlock here. The next statement is I'm going to return from this function. When I return from the function, all of my local variables go out of scope, their objects and their life. That lock guard named lock, its life ends. During its destructor, it will unlock the mutex. I can remove this one. There's that unlock sitting there in the catch of my try catch block. Same deal. My next operation is going to be rethrow the exception. This function is going to end, local variables get destroyed, my mutex gets unlocked. I can remove this one. Here we are down at the bottom. I'm about to return true. This function is going to end. My local variable is going to end its life. Its destructor gets called. My mutex gets unlocked. I don't need this one either. Let's look at this exception block again. I've got a try. I'm going to catch every exception that possibly comes out and immediately rethrow it. Why do I have these lines anymore? I can get rid of the exception handling here too. Now we're down to the safe version of the function we started with using an RAII class, and yet I won't ever leak that mutex. Now, of course, in a function that's, 8 lines long, this is easy to see. What happens if this is a function much larger that doesn't fit on a slide? And in 3 days, someone else adds a new early return into this function someplace. That RAII class keeps defending you and will keep ensuring that that mutex gets unlocked. This is the very important part of RAII. So throughout this entire example, I talked about variables with automatic storage duration. This whole thing isn't dependent on the C++ object lifetime, so however the objects start their life and end their life are applicable. So it doesn't have to just be local objects. I could do things such as create this worker thread as a std jthread, and I can push it into a vector. So now I can have this collection of worker threads running around. And now the lifetime of that object, since I moved it, is now however long it lives inside that vector. So eventually, when I finally do remove the object out of the vector, or the vector goes out of scope, as the case may be, that's when the thread will get joined. Now, speaking of storage durations, food for thought, you could do RAII with dynamic storage duration. But of course, that leads to the question that if you're doing a new of a std jthread, who's now responsible for that memory? So of course, you need to put that into an RAII. Let's not go there. Another poster child example of RAII, std unique pointer. If you're in the shared pointers talk 2 sessions back, you learned all about std unique pointer. Standard RAII class, its job, takes in a pointer and will ensure that it gets deleted when it goes out of scope. I would hazard say it's probably one of the most common RAII classes used. But even beyond unique pointer, there's std shared pointer, and that deals with what happens if you have multiple people owning the resource. Again, 2 sessions back, you get lots of details on shared pointer. Other standard RAII classes, things such as std unique lock. We looked at lock guard, which is very much begin end. Unique lock is a more sophisticated lock guard in that it can adopt a mutex that has already been locked by somebody. It can adopt a mutex and wait to be locked. You can ask it to unlock the mutex during its lifetime. But throughout the entire thing, when it hits the end of its lifetime, it will guarantee that the mutex gets unlocked. It will also guarantee it doesn't unlock it twice. Std jthread manages joinable threads. Recall that we used to have std thread, and that was one of the problems of std thread was that if you didn't join it when it went out of scope, bad things happened. Std jthread fixes this and says, when jthread goes out of scope, it will join the thread. That's RAII. The thread's a resource. Std fstream opens and closes files. Same idea. Some RAII classes may allow you to reclaim the responsibility from the object. In addition, you may have ways to merely get access at the underlying object. Back to std jthread, for example. Jthread lets you do some reasonable things with threads, but not everything. As an example, the standard provides no way for you to do a thread affinity. I want to tie this thread to this CPU core. The standard doesn't let you do that. However, it does provide a method where I can ask it for the thread handle, and it gives me back whatever my platform handle is, so now I can use platform tools to talk about the raw resource. But keeping in mind, when you get handed one of these raw resources, be very careful what you do with it. Particularly in the case of unique pointer and shared pointer, you really don't want to get a hold of that raw pointer and hand it off to some other RAII class. Remember I mentioned about ownership earlier? Somebody should be responsible and own this thing. When you hand this resource to an RAI class, you are handing it the ownership. You shouldn't be messing with that resource directly anymore. That's the RAI class's job. And then, as mentioning about breaking the resource out, there may be some cases where you literally are trying to reclaim responsibility for that resource from the RAI object. And note, I do also say some may do it because it's not possible for all resources. My lock guard, you can't pull the mutex back out of the lock guard. Stud shared pointer, you can't pull the pointer back out of the shared pointer because it doesn't make sense. Again, lots of details. The shared pointer talked 2 sessions ago. Does this solve the 3 problems I started with? Does this solve leaks? Caveat, remember that we're generally defending against Murphy, not Machiavelli. If someone wants to break this stuff, I'm sure someone can come up with some code to break things. Lots of it revolved doing get the naked pointer and hand it someplace else, particularly on leaking pointers. But when used in a reasonable manner, does this prevent leaks? Yes, because it guarantees it will release the resource when the object goes out of life. Does it solve use after disposal? If your resource is now literally held by this RAI class, and the RAI class is out of scope, thus you have no way about talking about it, it's hard to use it if you can't talk about it. So I'd argue, yes, if the variable's out of scope, out of its end into life, you can't use it anymore. Double disposal, same deal. The disposal happens during the destruction of the class, of the object. C++ won't, unless you're doing some really weird stuff, won't destroy an object twice. And if it is, you've got bigger problems. So yes, it solves that problem too. Low variables don't go to scope twice. RAI does not solve everything. Lots of times, if there are 2 resources that somehow need to agree with each other on something, RAI as the idiom is not trying to solve that problem. As an example, resource loops. Picture this, you want to create a doubly linked list. You store your next and previous nodes as shared putters, because there will be multiple things pointing to the same node, so I need shared resource handling. So the problem is that when I take my head node and I decide I'm done, I can get rid of my head node, so that shared pointer goes away. My first node is still pointing at my second node. My second node is still pointing at my first node. So in both cases, they still have a resource or a reference count of 1, so they won't go away because there's always someone responsible for this. RAI as a concept isn't trying to solve this kind of problem. It's focusing on the individual paths. Another example, deadlocks. Back to my mutex example. What happens if in one thread I grab mutex A and then mutex B? In a second thread, I grab mutex B and then mutex A. When Murphy comes along and decides to task switch at exactly the wrong time, thread 1 grabs mutex A, thread 2 grabs mutex B, thread 1 tries to grab mutex B but can't because it's being held. So it task switches back to the other thread. It tries to grab mutex A, but it can't because it's already being held. So now I got 2 threads eternally waiting for each other. And again, RAI as an idiom isn't trying to solve that problem. That's not to say that there aren't classes that do try to solve that problem. Stud scoped lock, which is in the standard library, does try to solve this problem, and in that particular case, you initialize that with both mutexes, and it's shared lock's responsibility to make sure they're both locked in the same order. But again, that's a more sophisticated RAI class. The idiom itself doesn't consider that. So what happens if you have a resource that you want to manage, but the standard doesn't know how to do it? If the thing you are trying to manage is already a pointer, the one that likes to pop into my mind, POSIX files. Right? It's a file star. Fopen returns you a pointer. If it's already a pointer, then you could use unique putter to manage the pointer for you. And the reason that happens is that std unique pointer is templated on 2 parameters. One is the type it's holding, And the second one is a custom deleter, which essentially ends up being something that can be invoked, being passed the pointer, and will dispose of the resource that's been passed. I prefer to use the phrase dispose rather than delete because I'm talking about resources, not memory. Yet that custom disposal does not have to call delete. And if I can put my pointer into a unique putter, then I already get a lot of the RAII stuff essentially for free. Initialize during acquisition guarantees it gets destroyed at the right time. It will even prevent me from accidentally copying my RAII class around because this is a unique putter. It represents unique ownership. There can only be one. And even if you do an assignment, at least temporarily, there has to be two of them. And that's just bad because at some point they're both going to go to scope and there's that double deletion problem. So a unique pointer prevents you from doing that at all. So let's assume we want to manage a file star. So as a reminder, this is at least more or less what the Fopen and Fclose functions look like. Some standard libraries add in like restrict and a few other interesting things. But essentially, you have your Fopen and your Fclose. How do I get this into a stood unique pointer? Well, let's play with a little bit of boilerplate code. I can write a file closer function object. So it's a struct, it has the operator parens, and it takes one parameter, which is a file star. It's a const method because consts are good. And it fcloses the stream it's been handed. Then I can create a using declaration to say, hey, I'm making this thing called a C file. It is a unique putter of file and file closer. And thank you, Timur, for showing me this next one. In C++20, this gets easier because I can do a decl type on a lambda. So now I can do stood unique pointer of a file and the decl type of a lambda, which takes a file star and calls fclose. So now I've done all my background work to get my unique pointer in place. Let's be nice and follow the pattern of what the standard library does. Let's make a dedicated function to make a C file. So I've got a new function, takes the same parameters as fopen does, because I'm just going to turn around and call it anyway. Declare that local variable of file star stream, it's the one that actually calls fopen. I then test to make sure that my fopen succeeded. And if it didn't, I'm choosing to throw in an exception. As it turns out, this actually makes my destructor side easier. That lambda doesn't have to consider that I might be fclosing a null. I just throw an exception in this case, so it just can't be null. It always has a valid value. And I return a constructed C file, so I'm just returning the RAII class itself. And with this, I can now do the same sorts of things that we tried to say about new and delete in well-formed, call it modern C++. You shouldn't have to utter new and delete in the context of unique pointer. With this, I can do the same thing and say you should not have to ever call fopen or fclose. You should only have to call make C file and let whatever that variable is end its life. So using this example, I can put this all together. I have a function, auto file, make file of whatever file name, opening it for write. And now I can fprintf, but I do have to say file.get. That's the piece where I'm getting the underlying resource. And as a side note, anytime someone does a .get, that should be a yellow flag on the play. Why are we trying to peek under the covers? It's not necessarily a problem, but it's someplace to pay attention to during code reviews to make sure that they don't take that pointer and send it someplace else you didn't mean. Take copy, put it in a container someplace. I'll look at it later when that local variable goes out of scope. Question online.
All right. What about the implementation around slide 35? Why not use a class and put fopen in the constructor and fclose in the destructor? What are the advantages of a smart pointer over a dedicated class?
That's actually coming up in a few slides when we start talking about dealing with resources and you don't want to take the shortcut of using unique pointer, where you start constructing your own class. Yeah, so fprintf passed the file, we're good. Stood shared pointer has the same facility. It also has a custom disposal method. So if you want to have a shared file handle, you can do a similar thing here. I'm not going to show the details, but it's similarly not a whole lot of boilerplate, and you get the shared thing for free. And then you want to go on to handle something else. You want to handle your own RAI class. There's some design decisions you might want to consider when writing your own class. Is there a valid default acquisition to your class? Something to the, I'm talking about default acquisition. Provide a default constructor. An example of this might be, I want to write an RAII class to manage the startup and the initialization and shutdown of Windows WinSock. So my construction of my object is called WSA startup. During destruction, WSA shutdown. Because it's the default thing, we got everything we need. It does not preclude an empty state, which we'll get into next. Is there a valid empty state? Things like stood unique pointer has a valid empty state. It doesn't hold a pointer, it holds a null pointer. If your RAI class has a valid empty state, that's something to be aware of in your destructor, that you may not be currently holding a resource. Write your destructor accordingly. And to the question that came in online, you could provide a constructor with its own set of parameters and use that to parameterize the call to fopen. So you could do the same thing. Do you want to be able to adopt a resource? With that file example, particularly the user-defined RAI class file, do you want to be able to get a file star from somewhere else and put it into this object? And if you do, again, provide a constructor for that. Also does not preclude an empty state. And again, may need to understand the resource released early. Is your object copyable? Does it make sense to copy your resource? What does it mean to copy a file star? Do you really want two different file stars with the same file, or do you want a shared ownership? For example, a shared pointer, you can copy those all you want, because implicitly it's a shared ownership membership concept. So when you copy it, now there's two shared pointers pointing to the same thing, three shared pointers pointing to the same thing. Unique pointer is not. As a little bit of an aside, now is a good time to remind people about the rule of 5. As a reminder, if you need to mention any of copy constructor, copy assignment operator, move constructor, move assignment operator, or destructor, it is likely you need to mention all of them. And in this particular case, in RAI, I'd almost hazard to say you must, because it's almost guaranteed you are doing something special in the destructor. And if you're doing something special in the destructor, you're going to need to consider that in the other 4. So hence here, if you don't want your object to be copyable, declare your 2 copy operations as deleted. Similarly, same question for movable. Should your resource be able to be moved around someplace? Should it be able to be moved into a container? If not, delete your move operations. Be explicit of what you can and can't do with your resource. It is possible you may even have to delete both your copy and your move operations. For example, stood scoped locked, you can't. It is immovable, it is uncopyable. It's literally a scope-based lock. Make sure the user doesn't do it. However, shared pointer is movable. Shared pointer is copyable too. Unique pointer, movable. But it's a consideration you need to have. Do you want to let your users get at the underlying representation? Because if they can get at the underlying representation, you are providing a possibility that they may take that and hide that away someplace else and start opening up that possibility to your use after deletion or double disposal. So for example, stood JThread, you can get a hold of the thread handle because you might need to do operating system things with it. Scoped lock does not. It doesn't give you a way to get at the mutex. Do you want to hide the underlying representation altogether? Don't give them away a get at it, but that does mean that you now need to provide member functions of your own to gain access to whatever you want to let them do to that underlying representation. The bonus here is you no longer have to do that .get everywhere. Also, again, feeds back to the online question. If you write your own file star wrapper, RAI class, you'd want to provide your own read and write methods, and then internally, they'd have access to the file star to do whatever they needed to do. Even if you're trying to hide it, you may still want to let people get a hold of it anyway, because they might come up with something they may want to do that you hadn't thought of. But, like I was mentioning earlier, but if people are starting to use that underlying handle, that should be a yellow flag in the play that, well, doing something a little weird, be careful what you do with that. Interesting idea is dependent resources. What happens if you have an RAI class around something like a SQLite database? So it's managing the opening and closing of the database, all nice. But now you want to start a transaction on this database. You may not want to give them a start transaction call that returns a pointer to a SQLite transaction. Maybe you want to write your own SQLite transaction RAI class to manage its, that's a resource, have it managed, and your start transaction in your database class returns an instance of that RAII class. Prevents that naked resource from getting out from underneath you. Do you want to provide a way for them to get the resource out of you altogether? Such as stood unique pointer's release method. You get your pointer back, unique pointer now holds null. You may not want to let them do that. The Mutex one, for example, doesn't. Shared pointer can't. You might want to consider even marking that particular method as no discard because you're explicitly asking that RAI class to relinquish its responsibility. It's handing the ownership back to you. You should do something with this. You really don't want people to call .release as the only thing on the line, so you get back the pointer and it drops it on the floor, because that's going back to leaking. An example RAI class I have had to write in the past, unique unlock. It's actually the reverse of a scoped lock. I want this thing to unlock a mutex during construction and lock it during destruction. I happen to be using this during a work queue implementation. So I'd have the mutex locked while I was pulling something off of the queue. Then I want to unlock the mutex so other threads can push more things onto the queue. I do my work, but I want to make sure that I'm locked again before I come back and look at the queue. So in this case, I have a unique unlock. I've templated on whatever my mutex type we want to put in there. I have my explicit constructor that takes a stood unique lock of that mutex. So that way I can guarantee I'm being handed a locked mutex. Store the reference because I have the unique lock as a reference member variable. And during my constructor, I unlock the mutex. In the wonderful commented area, I delete the copy and move operations because I don't want people to move my resource around. And during my destructor, I relock the mutex, which of course will block until I actually acquire the mutex. Which means I end up with something like this. I have my mutex somewhere outside of my function. I have a unique lock. I do something that I need to do protected by mutex. I create my little scope to say, here's my unlocked area. Do whatever I need to be unlocked. When it locks again, I might need to do more work protected by the mutex again. Reestablish that whatever state got mutated is where I left it, because mutex is unlocked, so there's certain preconditions that no longer hold. Here's my plug for the C++ core guidelines. RAI says all sorts of good things that even the core guidelines has a number of items to say. For more information on the core guidelines themselves, Rainer Grimm is talking about this on Thursday. The entire R section on resource management, which basically kind of a short synopsis. Don't use new, don't use delete. Use make unique, use make shared, use unique pointer, use shared pointer. And because all these things are dependent upon the scopes of variables, that I've also listed some of the items about scopes. like ES5, keep your scopes small, particularly in the case of the mutex example I've got. You don't want to lock your mutex early, and you don't want it to hang around long after you've needed it. You want your mutex to lock at the right time and unlock at the right time. Always initialize an object. That's part of the resource acquisition is initialization part. Don't introduce a variable before you need to use it. Back to the mutex example. I really don't want to lock the mutex at the top of my function, do a bunch of other unrelated things, now do the stuff that should be protected. Yeah, but I want that mutex locked as close to where I need it as I can. Don't declare a variable until you have a value to initialize it with. Like, these are good ideas for variables in general, but because the resource management pieces are now tied to the lifetime of a variable, these get additional considerations. So at the end, RAII, resource acquisition is initialization. Acquire a resource during the construction of an object, or hand it a resource. Dispose of it during destruction. Thank you. Questions?
A question I have is, especially I've seen this when trying to wrap C APIs, acquiring the resource in the constructor is usually pretty straightforward, but for those cases where releasing the resource can fail, how do you deal with that in the constructor?
So essentially the question ended up, what happens if releasing your resource could possibly fail, particularly in the context of C APIs? That's just trouble all around. Because it's a destructor and you can't stop it from happening, that would imply that your only real mechanism of reporting that error would be to throw an exception from the destructor. And exceptions escaping destructors, while not technically illegal, tends to end up being a lot of trouble, particularly if it ends up having to destroy this while there's already an exception in flight and your program ends. I'm not sure RAI has a good answer to that, just because the resource going out kind of has the same sort of assumption of destructors in general, that you can't really fail to destroy, you can't really fail to release the resource. And in some cases, that does raise the question, what does it mean for a resource to be failed to be released? So I'm not sure that's a particularly satisfying answer, but yeah, I think destructor is the only viable answer. The only slightly better or less objectionable answer is writing state out to a global variable, and that just makes me itchy. I hate.
Notice that here in the example, fclose actually has a return value.
Yes, and I'm actually ignoring. Yeah, sorry. You were mentioning that fclose actually does have return value, kind of along the same lines that printf has a return value. Who actually checks it? Good question. I've been ignoring it, but it's a valid question. Yep.
Does the standard library implementation of the Mutex depend on the operating system's Mutex?
Yes. Essentially, it's the question was, does the stood mutex depend upon the operating system's mutex? And while, okay, I suppose my initial definitive yes is overreaching on my part. I would strongly suspect yes, because stood mutex is a little less, has fewer constraints than, say, stood recursive mutex. That your stood mutex might be recursive if the operating system one happens to be, but it won't guarantee it, so it's not safe to assume it's recursive, for example. But I would expect that a stood mutex almost directly maps to whatever the default mutex is on your operating system. Oh, there we go. Sorry, a light that blinds me. So the question was, what happens if you have a static object as an RAI class? Really, the consideration is that the RAI class acquires when it's constructed, whenever that happens to be, and is released during its destruction, whenever that happens to be. So if we're talking about global static objects, That would imply that it's being constructed sometime before main and is destroyed sometime after main. And I'm being deliberately vague about exactly when that is, because then you start running into what tends to be known as the static object initialization fiasco, in that if you have static in translation unit A, another static in translation unit B, it is indeterminate which one gets initialized first. The only thing you do know is that whatever order is chosen, they get undone in the opposite order. So if you're acquiring a resource has some of these dependencies, that could be trouble for global statics. If we're talking about function level static local variables, same deal. The first time the flow of execution crosses that static local variable, it gets constructed, acquire your resource. And then, if I recall correctly, it's sometime after main, but I think it's before the global statics, it will get destroyed. On the plus side, welcome in C++ 11 now and beyond, if that is called from multiple threads, it is guaranteed to only be initialized once and done so in a thread-safe manner. And I think it's the only other static options that are interesting.
Yeah. Are there any situations like not to RAII, or we need to take extreme careful using?
Are there any situations where you wouldn't want to RAII? Possibly. If your release of your resource could fail, RAII could be a problem in that you can't deal with the failures, not nicely anyway. So that might be a case. If somehow you can't map your resource lifetime to the C++ object lifetimes, that might be another reason why you might not want to create an RAI class. But generally, as a default, you probably want to try finding a way to do RAI precisely because the language guarantees that things will work properly. It doesn't rely on the developer being excellent because, of course, none of us write bugs. Doesn't happen. And back.
How is RAII different than value semantics? Or is value semantics just an extension of RAII?
I unfortunately did not see that talk. So I don't think I can speak intelligently to that. Sorry, the question was, how is this RAI different than value semantics? I unfortunately didn't see that talk, so I can't speak intelligently to that. Although somewhat related to that, Daniela's C_wrapper, I think it was called, is an RAI class. It's just a little more sophisticated than what I showed. Because she had encoded the acquisition and the destruction pieces in the template parameters, which is interesting. Anything else?
It's not completely related to the talk, but it's been on the back of my mind since I've seen it in a few talks. You use the using keyword almost to do a type def.
That is a type def. Well,
yeah, I was going to say, the question was, why using instead of this type def, the type you want to alias and then the name you want to give it?
why use a using declaration versus a type def? Okay, don't quote me exactly, but a using declaration can cover more cases that a type def can't. As I recall correctly, you can do a using declaration to partially specialize a template, which you can't do with a type def. And then as a result, for consistency's sake, doing all of your type aliasing with using becomes useful. Anything else? If that's it, thank you very much.